Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll describe the formulas for calculating a correlation coefficient. Before we learn how to calculate the correlation, you must learn what a covariance is. We are familiar with the concept of a variance, which tells us how a single variable varies. The covariance tells us how two variables vary together. Let's examine these formulas. Recall that the sum of squared errors is the sum of the squared differences between each score and the mean. The variance is the sum of squared errors divided by n minus 1. The covariance formula is the sum of the product of errors for x and y divided by n minus 1. This means, first, the difference between observed score and mean is calculated for every score on x and y. Then, for each person, their error on x and error on y is multiplied. The sum of all these products is the numerator of the covariance. Squaring the differences in the sum of squared errors, which is the numerator of the variance, essentially means multiplying each difference by itself. In the covariance, instead of multiplying each difference by itself, we are multiplying the two differences together for two variables. The correlation coefficient between two continuous variables has the full fancy name of the Pearson product moment correlation coefficient. It's named after Karl Pearson, a very famous statistician. Now, remember that the correlation is the standardized relation between two variables. So to calculate the correlation coefficient, we need the standard deviations of x and y. We also need the covariance between x and y, which I just showed you. The covariance between x and y is the numerator of the correlation coefficient. The denominator of the correlation coefficient is the product of the standard deviation of x and the standard deviation of y. You've learned how to calculate each of these three statistics already. This is what we use to calculate the correlation coefficient. These formulas also relate to calculating z-scores. Again, remember a correlation is a standardized measure of association. Recall that an individual z-score is the observed score minus the mean divided by the standard deviation of that variable, and we have z-scores for each person. If we rearrange the correlation equation, the correlation coefficient could also be calculated by averaging the product of z-scores for x and z-scores for y, and adjusting the denominator to n minus 1 instead of just n. We most often use the first correlation equation because it's computationally easier. We will go over examples of computing correlations in class. The size of the variability of variables can have an effect on the size of the correlation. If your variables can take on any value, x and y do not have a restricted range. But some conditions don't allow for the full range of scores. If a variable doesn't have the full range of scores, for example, if x values only fall on a restricted range of potential scores, then x would have a lower variance, and this would lead to a lower correlation or no correlation between x and y. Let's do an example to illustrate the restricted range problem. Here, x is IQ and y is happiness. Here's a visual depiction of what the scores would look like for a full range of IQ. If we look at the population where the whole range is present, we see a positive relation. Let's say that we have limited the values that IQ occupies due to poor sampling. Here is an example of one way you could get restricted range. There is a lot of variability in the population when it comes to IQ, but perhaps we've selected a sample where there's less variability. For example, if you select your sample from an elite private school and you measure IQ, you may find that there's less variability in IQ. Perhaps due to admissions criteria, this sample tends to have high IQ scores. So we just get the scores to the right of the dotted line in this figure. We have reduced the potential variability in the scores. This is restricted range. Now the relation is obscured. If you were to compute a correlation between IQ and happiness just in your sample, the correlation would be lower in magnitude relative to if you computed the correlation in the whole population where the full range of IQ is represented. Thus, restricted range can lead to a lower correlation. Lower meaning smaller in magnitude as opposed to negative. We just covered how restricted range can reduce the size of a correlation, but other things can also influence correlation coefficients. For instance, the presence of an outlier could bias the correlation coefficient. It's also the case that a correlation coefficient may not be appropriate for your data. A Pearson correlation is meant to describe linear relations only, and some relations aren't linear. We could model them with other things, but it's not appropriate to calculate a correlation coefficient for non-linear relations. There are many forms of nonlinear relations, but I'll give you an example of one type, a quadratic. Some developmental scientists have hypothesized and found a quadratic relation between negative emotions expressed by parents in the home and children's emotion understanding. If there is hardly any negative emotion expressed in the home, kids might not do a good job recognizing anger or sadness in other people, or what types of situations elicit anger and sadness, because they never see anger and sadness in others. If there is a lot of negative emotionality expressed in the home, kids might have a distorted view of anger and sadness, or what things normally elicit anger and sadness. For kids with no, or for kids with lots of exposure to negative expressivity, they might have poor emotion understanding. On the other hand, if they see normal amounts of appropriate negative emotionality expressed, they may get a good understanding of emotions. This pattern of association does not follow a linear pattern. Rather, it's quadratic. If you observe in a scatter plot that two variables are non-linearly related, a Pearson correlation should not be used to summarize that relation. Instead, you'd use some other model, for example, regression with a quadratic term. This concludes the third lecture on correlations. In the next lecture, I'll describe types of correlations for variables with non-continuous measurement scales.